How's it going, everyone? In this video, I'll talk about matrix multiplication, okay, specifically multiplying a matrix by another matrix. And this is related to the vector dot product, right? So just as a reminder, if you have vector u, and let's say that's equal to u1, u2, u3, and so on up to un, and you have vector v, okay, which has the same dimensions. It's equal to v1, v2, v3, and so on up to vn. You take the dot product between them, and you're just going to multiply all the corresponding components with each other and add the result up, right? So you're going to have u1 times v1 plus u2 times v2 plus u3 times v3, and so on up to un times vn. Okay, and if you want to write it in summation notation, you could write it like this: ui times vi. Okay, so that's the vector dot product, and we're going to use that to explain how multiplying a matrix by a matrix works. Okay, you can think of a matrix as a set of vectors, either column vectors or row vectors. So for example, let's say you have a matrix like this: 3, 2, 1, -2. Okay, you can think of it as something that looks like this. Okay, u and v, where u is equal to 3 and 2, and v is equal to 1 and -1. Okay, so u and v here are row vectors. Each vector is a row of a matrix. Alternatively, okay, you can think of this as being equal to vector A and then vector B, where A is a column vector 3, 1, and B is a column vector 2, -2. Okay, so this matrix has two column vectors next to each other, 3, 1 and 2, -2. When you're multiplying a matrix by another matrix, you're going to multiply the row vectors of the first matrix by the column vectors of the second matrix using the dot product. Okay, and it's going to look like this. Okay, let's say you have so let's say 3, 1, 2, -2 multiplied by 1, 2, 3, 4. Okay, so the result is going to be a matrix, okay, and every component of that matrix is going to be a specific dot product. So if we take, okay, we have these two column vectors in the first matrix, we have these two row vectors in the second matrix, and we're going to take the dot product of every combination between a row vector and a column vector. Okay, so our first combination, and I'll use a different color here so it's easier to tell, our first combination is this. Okay, the dot product between these two vectors, that's going to be 3 times 1 plus 1 times 3, right? So this times this plus this times this. Okay, that's going to be the first row, first column of the resulting matrix, okay, because we're using the first column vector and the first row vector. All right, so what about the first row, second column? Well, that's going to be the first row vector dot product with the second column vector, okay, and that's going to be 3 times 2 plus 1 times 4. Okay, so 3 times 2 and then the 1 times the 4. All right, what about the second row, first column? Well, that's going to be our second row vector multiplied by our first column vector. Okay, so we're going to have 2 times 1 plus -2 times 3. Okay, and what about our second row, second column input? Well, that's going to be our second row vector dot product with our second column vector. Okay, that's going to be 2 times 2 plus -2 times 4. All right, so as a result, what we end up getting is, okay, so 3 plus 3 is 6. 6 plus 4 is 10. 3 minus 6 is negative, sorry, 2 minus 6 is negative 4. And 4 minus 8 is going to be negative 4 as well. Okay, and that's our answer. So that is vector multiplication, right? Now, here's the thing. What if we multiply them in a different order, right? So let's say this is vector A right here, matrix A. This is matrix B right here, right? So matrix A times matrix B is this. What if we were to do matrix B times matrix A? Okay, well then we have 1, 2, 3, 4 multiplied by 3, 1, 2, negative 1. Okay, so what does that give us? Okay, so our top entry, right? First row, first column, that's our first row vector, first column vector. Dot product between them, all right? So that's going to be 1 times 3 plus 2 times 2. Okay, first row, second column, that's going to be our first row vector with our second column vector. So that's going to be 1 times 1 plus 2 times negative 2. All right, second row, first column, right? So second row vector with our first column vector, these two right here. Dot product between them, that is 3 times 3 plus 4 times 2. And then our second row, second column, that's the second row vector with the second column vector dot product, and that will give us 3 times 1 plus 4 times negative 2. Okay, so what do we get as a result? Okay, so 3 plus 4 is 7. 1 minus 4 is negative 3. 9 plus 8 is 17. And 3 minus 8 is negative 5. So you'll notice that these are not equal to one another. Okay, so order matters if you're multiplying matrices, right? So when you're multiplying matrices, A times B doesn't necessarily equal B times A. It might equal, right? Sometimes it does, but not always. Okay, so this isn't necessary. Okay. Now, you know what? I wrote that really messy. I'm just going to erase it. Okay, so it's not necessary that A times B equals B times A. Now, to write this more generally, okay, so let A be equal to a set of row vectors. Okay, so let's call this A1 is a vector, A2 is a vector, and so on up to AN, which is also a vector. All right, so you have, and it's a vector, right? So this represents a whole bunch of numbers, right? And each one is a row. Okay, and B is going to be a bunch of column vectors. Okay, so we're going to have B1, B2, and so on up to Bn. Okay, so then A times B is going to equal a matrix where every entry is a dot product between the corresponding row vector and column vector, right? So first row, first column, that's going to be A1 dot product B1. Okay, first row, second column, A1 dot product B2, right? And so on. And then A1 dot product Bn is going to be our first row, last column. Okay, as we move down, so second row, first column, that'll be A2 dot product B1, right? And so on until we get to AN, dot product B1, that's our nth row, first column. Second row, second column, right? A2 dot product B2, and so on, right? And our last row, last column is going to be AN dot product BN. Okay, so that's just the more general way of writing it. Now, you'll notice that the dimensions match up here, right? Like we have n row vectors in matrix A and we have n column vectors in matrix B. And that has to be the case for matrix multiplication to be possible. Okay, so for example, let's say we have something like this, right? A matrix where we have 3, 2, negative 1, 1, 1, 7, 2, 1, right? And we want to multiply that. So notice we have 2 row vectors, okay? We have 2 row vectors here. So we need 2 column vectors, okay? So we might have something like this. So 2 column vectors and, we have 2 row vectors, but they're each of dimension 4. Okay, so we have 4 components in our column vectors, so we're going to need 4 components to our row vectors. So for example, something like this, like 1, 3, 5, 2, negative 3, 0, 2, negative 1, 6, and 1, 2, 7. Okay, so our row vectors are 4-dimensional. Our column vectors that we're multiplying by are 4-dimensional. So we can actually calculate the result, right? So it'll be this dot product with this, right? And then that top row, and that will go here. Then we take that row dot product with the second column, the answer will be here, and that dot product with the third column, and the answer will be here. As for the second row vector, dot product with the first column, the answer is here. With the second column, the answer is here. With the third column, the answer is here. Okay, so you'll notice that the dimensions of our first matrix was 2 rows, 4 columns. The dimensions of our second matrix was 4 rows, 3 columns. And we need this to match up, right? The number of columns of the first matrix has to equal the number of rows of the second matrix so that you can take that dot product, right? Your row vectors, which are in your first matrix, they have to have the same dimension as your column vectors that are in your second matrix. And what's the result that you get? Well, you get a 2 rows by 3 columns matrix, and notice there's your 2 right here for your 2 rows, and there's your 3 right there for your 3 columns. Okay, so the dimensions of the matrix have to match up that way for matrix multiplication to be possible. Okay, so for example, okay, let's say A is a 5 by 3 matrix, and B is a 3 by 2 matrix. Okay, well, the dimensions of the rows of A is 3, and the dimensions of the columns of B is 2, which means you can multiply them, right? So A would look something like this, right? 5 rows, 3 columns. Each of these dots represents some number. And B looks something like this, 3 rows, 2 columns, right? And you can multiply them, okay? Because you can take the dot product of this with this, and you'll get a number there. The dot product of that same thing with this, you'll get a number there. And then you can repeat that for all the other rows, right? And you'll get a 5 by 3 matrix. 5 by 2 matrix, right? There's your 5, there's your 2, the 3's have to match up. But notice that even though you can calculate A times B, you can't calculate B times A, right? You can't calculate this, right? Because B times A will look like this, okay? There's B. Again, every dot represents a number. There's A. And you can't take the dot product of a two-dimensional vector with a five-dimensional vector. You can't do that. So not only is A times B not necessarily equal to B times A, right? But A times B might be possible, right? You might be able to multiply two matrices in one order, but B times A might even be impossible. You just can't even multiply them in that order. Okay, so that's another thing to keep in mind for matrix multiplication. Okay, and that is how you multiply two matrices together.